Assalamu alaikum everyone. Uh, it's an interesting topic. I think all the inspection departments are used to face this challenge. Like if inspection is done and if any equipment is found with some defect, what we need to do further. So API 579 is the answer. What is fitness for service? Like if in academic terms, the ability to demonstrate structural integrity of an in-service component containing a flaw or a damage. Component is or has been used. It's not like new. There is a defect in the component, and we need to consider current integrity of the equipment. It also used to determine what is the remnant life of the equipment. Objectives. Basically, when we say FFS is a multidisciplinary exercise. Mainly, three resources are required. First of all, the inspection engineer or inspection people who determine the condition of the equipment. Number two, there would be corrosion knowledge required, I mean corrosion engineers are required or material engineers are required to support. And number three, people who understand ASME and API 579 engineering formulas calculations, right? So FFS assessment is a multidisciplinary approach to determine whether an equipment which is suffering from flaws or damage or subject to operating conditions higher than design loads is fit for continued service or not. Final outcome of FFS is a decision to run as it is, repair it, re-rate it, change it, or retire the equipment. FFS results can also include an estimate of the remnant life, which is useful for planning of the future decisions, including inspection as well as the retirement. So benefit of FFS study are there, of course, like if equipment is having a defect, then what we need to do. There should be some proper guidelines. API 579 has provided that guidance and platform to execute the exercise to make the next decisions. Number one, improve safety and reliability of aging operating equipment, reduce downtime by eliminating unnecessary repairs, better planning of shutdown and replacement of equipment, improved yields if rate of equipment deterioration or life consumption can be estimated or extended. So there are multiple areas where multiple defects where FFS can be applied. So corrosion, stress analysis, metallurgy, material engineering, non-destructive examinations, plant operations, fracture mechanics, probability and statistic analysis. These kind of expertise are also required or would be useful. Application point of view for pressurized equipment, which are built to ASME 8, Division 1 and 2, ASME B31.1, 31.3, API 650, 620. All equipments can be covered for FFS assessment. Pressure containing equipment built to other recognized codes and standards like BS 5500 can also be assessed. Intended to supplement and augment the requirement of other codes such as API 510, API 570, 653. In general, if equipments are meeting API 510, 570 and API 653 criteria, FFS assessment not required. FFS requirement starts if equipment is not meeting or piping system is not meeting the criteria of API 510, API 570 and tanks are not meeting the criteria of API 653. This general concept. The background of FFS assessment. In 1990, Joint Industry Project was organized by the Material Properties Council MPC in states to develop FFS guidelines for the refinery industry. In 2000, based on MPC final report, API issued a API 579 recommended practice for FFS assessment, which was welcomed by both refinery and non-refinery industries. In 2007, ASME joined forces with API and issued API 579 and ASME FFS-1 standard. 2016, latest edition was published in June 2016. So there are various sections in API 579. The major one where people normally use extensively are Part 1, Part 5, Part 6, Part 7. And brittle fracture, Part 3 and Part 9, crack-like flaws, Part 9, fire damage under Part 11 as well as 4, 5, 8, 9 and 10, creep damage under Part 10, mechanical damage under Part 5, 8, 9, 12 and 13, fatigue damage under Part 14. So API 579 is quite big standard. It requires extensive knowledge to use it. Mainly people with mechanical background or chemical engineering background can use it easily, but they should have some design experience from past. So this is basically the front page of API 579. So those same chapters you can see here, like general metal loss is under Part 4, localized metal loss under 5, pitting Part 6, then crack-like flaws under Part 9. So fire damage under 11. So since time is lesser, so I'm just giving you the outline. So there are some annexes also. Good guideline is given the standard and it's not difficult to use. Luckily, I have been using this standard since 2000, so we have done many jobs. So for me, it looks very easy. There are various levels which are involved under FFS assessment, like simple is level 1, moderate is level 2, and finite element analysis, which is normally done with the help of any software, is level 3. Under simple, like minimum amount of inspection and information should be available, conservative screening criteria, comparison to the original code performed by inspectors or engineers. If results are not acceptable, can advance to the level 2 and level 3. In level 2, more detailed evaluation, more detailed calculations performed by experienced engineers, more precise results. If results are not acceptable, advance to level 3. Level 3, rigorous evaluation, detailed inspection and information is required based on numerical techniques such as FEA and most precise results. I would say not so precise, but up to a certain extent, it can give more allowance to use the equipment. In general sense, if people who are the layman knowledge, like if equipment is basically failing under API 510, let's see a pressure vessel. So then under level 1 or level 2, we can see like if the defect is or metal loss is greater than basically acceptable limits of API 510 or ASME 8 division 1. So you can always take help from ASME 8 division 2. If you see the allowable stress values allowed in ASME 8 division 1 and ASME 8 division 2, there is a 16% basically allowance available between division 1 and division 2. So normally under FFS, that 16% allowance is taken care, and then under RSF, there is a factor of 0.9, it means 10% further. So up to certain extent, if a layman terms, we can say there is an allowance of 25%, almost 25% allowable stress from the yield stress, which could be used depending upon size of the defect. Any questions up to now? Okay. So now, just one technical aspect, which is as a raise hand, 2 parts. Okay. So RSF is estimated by equation for level 1 and level 2 assessments and computed by nonlinear FEA in level 3 basically. RSF is LDC over LUC. RSF equal to remaining strength factor. LDC is limit load of the damage component. LUC is limit load of undamaged component. RSF is compared with an allowable value of RSFA. If RSF less than or equal to 0.9, then basically equipment is acceptable. If lesser, then re-rating is required. This is a normal concept. So now we are going to a case study, what we have basically performed for a CBA reactor. We covered level 1, level 2, level 3 FFS, and corrosion prevention study for these CBA reactors. These CBA reactors are normally used under basically sulfur recovery units of class process, and these are used extensively in the industry. Study objective was fitness for service assessment of CBA reactors in accordance with API 579, identification of applicable damage mechanisms, and preparation of recommendations for corrosion prevention program. Then development of recommendations and monitoring plan, and or for permanent repairs as well. So the steps for the study: flaw and basically damage mechanism identification, applicability and limitation of the fitness for service assessment procedure, data requirement, assessment techniques and acceptance criteria, remaining life evaluation, if there were any remediations, in-service monitoring, documentation. CBA reactors process. In the CBA process, one CBA reactor is used for a period of time, almost let's say for 24 hours, to conduct the clause reaction at low temperature with absorption of produced sulfur on the catalyst. Then, before the catalyst in the CBA reactor is basically adsorbed, level is increased and its equilibrium level is reached, then regeneration of the same catalyst is required by feeding hot gas to reactor, which heat the catalyst and vaporize the adsorbed sulfur. When regeneration is complete, the CBA reactor is cooled, which is accomplished by the flowing a cool gas, a gas stream through the catalyst bed. When catalyst bed has been adequately cooled, the CBA reactor is again used for low temperature clause reactor with adsorption of sulfur on the catalyst. The two CBA reactors function in a cyclic fashion between the lead position and the tail position. CBA reactor operating conditions are divided into cyclic cycles as below. The normal operation, when we say low temperature, is not so low, it's 120 degrees Celsius. Operating pressure is 1.4 bar G. Regeneration of the catalyst operating temperature is 343. That's the big difference between both, and operating pressure of 1.4. If you see the temperature ranging between 127 to 343, it basically created thermal expansion issues as well. And in the reactor, if you want to add basically cladding, so cladding material and the base metal like carbon steel, SA 516 grade 70 and SS 316L, both would have a different thermal expansion coefficients, and cladding is practically not possible. Similarly, there is an issue with the ceramic lining as well. That is not possible. So solution-wise, client was using aluminizing, and that also faced problem because of this thermal expansion coefficient differentials. The main focus on this study is these two temperature changes, which occurs once in 30 hours, right? So the data for these basically standards, and the data, some data has been changed, but so it should not be correlated with actual study to protect the basically confidentiality of the client. However, the required information has been maintained. The code for the vessel was ASME 8 Division 1. Commissioning date was 1994. Design condition 3.5 bar. Pressure and in design and operation was 1.4. Inside diameter 3.7 meters. Nominal thickness 16 and 28 at various locations. Colonial allowance 5 mm for the nozzle, 6 mm for the basically shell and some nozzles. Material of construction SA 516 grade 60N. Well joint efficiency 1. Time for one thermal cycle 30 hours. Number of cycles in 25-year service 7,000. So this is the GA of the vessel, the horizontal vessel, quite big one. List of the reactors and defect summary. There are basically 6 reactors. Tags are there, but number changed. So groove depth at various vessels, maximum 8, minimum 4. Groove length varying from 2200 for vessel 3 and 1300 for vessel 1 or reactor 1, and the minimum is 470. Groove locations at the various shell numbers are given. The minimum thickness measured 12 mm, nominal thickness 16 mm. So where you can see the difference between 16 and 12 is 4 mm, but some groove depths were 8 and 6. So those grooves were basically repaired with weld overlay and considered closed. Otherwise, the FFS scenario for those deep grooves were giving negative results. Inspection year 2016. So minimum 9.4 and 10 mm thickness was measured for 2 locations during the inspection. So this is the location of the spread of the defects on the GA of the vessel. Yeah. So these are, if you see, the defects are more near to nozzle number 1 and nozzle number 2, and you will see the cause of these defects, like flashing of the product when it is coming inside the reactor, could be causing some dew point, low dew point for the water content of the acid gas, and those water content might be causing some heavy corrosion. So these other location of the defects which are showing near to the basically weld seams. These are the seams of the welds of the various courses, and these are some locations there. Okay. Now, summary of the historical records. Class sulfur recovery is enhanced by cold bed absorption reactor. CBA reactor undergoes cyclic temperature operations resulting in multiple corrosion mechanisms. During 2016 shutdown, deep pitting up to 8 mm location, localized pitting was observed in these vessels, and those were repaired by weld buildups. During 2016 shutdown, 4 mm corrosion recorded in V001, V002, no weld buildup repairs were done. Aluminized coating exhibit peeling off and internal corrosion grooving due to cyclic temperature operation. During 2016, CBA reactor internally lined inlet piping was upgraded to SS, basically 317. PLAD indicating upgraded piping is given on the next slide. So this was one of the learning lessons for the FFS team as well. If this lead clouded part of the piping was changed, right? So it means there was some issue with the carbon steel, which was not aluminized. So due to this reason, these vessels were facing basically this problem, and as a result of this FFS, similar kind of upgradation was also suggested as one of the recommendations. So now, identification of applicable sections of API 579. Section 5.1.1 contain assessment procedure for pressurized components subject to local metal loss resulting from corrosion erosion. Section 5.2.1 contain assessment procedure for types of flaws that are characterized as local metal loss, groove-like flaws in which length of the metal loss is significantly greater than the width. From inspection report, it is obvious that the defects recorded are more likely towards groove-like flaws. Therefore, API 579 section 5.1.1 assessment of local metal loss is applicable. That decision was drawn basically. As per section 5.4.2.1, level 1 assessment procedure can be used to evaluate component with local metal loss subject to internal pressure. As per section 5.4.2.3 D, if the component does not meet the level 1 assessment requirement, level 2 assessment should be considered, and vice versa. As per section 5.2.5.2, level 3 assessment can be performed. Level 1 and level 2 do not apply in case of the above section. component subject to internal pressure, external pressure, supplement, loads, or a combination of any. Component is a cyclic service, that's why level 3 is must. Now, following basically as per ASME API 579, if the number of cycles are more than 150 component cyclic service, then finite element analysis is required to be conducted in accordance with ASME 8 division 2. It's not listed here. So following software tools are used by us: Code, Compress, PV Elite, Signal FFS. Excel spreadsheets were also used for level 1 assessment. And these are the models which are used in 2 softwares or 3 softwares. The first one are from PV Elite and the lower one are from Signal. So following software tools are used. Now, various cases of the studies were conducted. Case 1 was ASME 8 division 1, a design analysis with 5 mm crane allowance on the shell and 6 mm crane allowance on the nozzles. Case 2, ASME 8 division 1 analysis, design analysis as a corroded vessel with defects. First one without defects. Case 3, basically API 5791, part 5, level 1 design analysis. Then case 4, fatigue analysis with 7,000 cycles. Case 5, fatigue analysis with 10,195 cycles. And case 6 with 13,140 cycles. We try to see up to which number of cycles can be acceptable for the cyclic service. In case 1, basically results now. Case 1, original design of reactor was found in compliance with ASME 8 division 1. Case 2, reactor was found in compliance with ASME 8 division 1 with 4.71 mm and 3.1 mm FCA, future crane allowance, for internal and external pressure respectively. Case 3, API 579-1, level 1 assessment was conducted and results are found acceptable for internal pressure case. Level 2 assessment was not required since the defects were accepted in level 1. Level 3 assessment is considered as a component is in the cyclic service. Case 4, ASME section 8 division 2, based fatigue analysis for 7,000 cycles, minimum threshold for the equipment to be in cyclic service. Results were found acceptable for all nozzles. Case 5, ASME section 8 division 2, based fatigue analysis for 10,195 cycles, assuming design life of 15 years. Results were found acceptable for all nozzles. Case 6, ASME division 2, based fatigue analysis with 13,140 cycles, assuming design life of 18 years. All nozzles were found okay except nozzle N3. It means that was the limit and nozzle 3 was identified as a limiting component. So these are some photos, like in 1 hour presentation, this is what I could show. Like the red portion is showing the nozzle which is coming under high stress. And this is the basically latest of the equipment or model what we have used. These are the some load cases which were run by the Signal software. Now the results of the case 4, you can see that like under load case 1, highest primary stress ratio should be greater than 1.5 SMH. So here the maximum load ratio is 57% in the case 1. Case 2, this is the ratio of the various loads. And case 3, highest fatigue stress ratio, which is shown for the various components, right? So this is the Excel spreadsheet what we used for the analysis, and these formulas are fairly available in API 579 section, basically part 5, and in a normal exercise we should be passing through the steps, but since 1 hour demonstration, so I could only show you the spreadsheet. Otherwise, maybe in the next detailed webinar we will go through the each step in more detail. So this is the result, and basically RSF was greater than 0.9. Really it was 0.9.71 and required is 0.9. So level 1 was okay. So under case 1, for example, if you see FFS results, if you see if the defect size, uniform metal loss 4 mm, 6 mm, 7 mm or 8 mm, and then longitudinal basically dimension of the flaw 50 mm, 100 mm, 150 mm, 200 mm, circumferential dimension of the flaw 100, 100, 150, 200. So if you see the RSF or remaining strength factor is 1.1, 1.1, 0.971 or 0.851. So the first three conditions satisfied, condition satisfied, condition satisfied, condition not satisfied. So in this way we can assign, like we can limit or identify the basically target defect length, like which could be acceptable up to what depth level. So in this way future monitoring of the equipment can be done easily. So level life calculations based on API basically 571 and criteria or 510 criteria. So if you could see net metal loss of each basically internal pressure and external pressure for one of the short-term corrosion rate and long-term corrosion rates. The nominal thickness was 16 mm, net metal loss 5 mm, 8 mm, 5, 8, remaining thickness. Basically, when we say 8 and 8, so these repairs were basically done. And the remaining thickness which was reported after repairs were 12 mm. So inspection interval 3 years, corrosion rate which is from previous inspection to new short term, it is 1.6 mm per year, 2.66 mm per year, 1.66 mm per year, 2.66 mm per year. So FCA 4.71, 4.71 for internal pressure, 3.12 mm, 3.12 mm for external pressure. So these are the short-term remnant life, only 1.87 years or 1.17 years remnant life was reported minimum. If metal loss is basically on the long-term basis, like this metal loss took place during the last basically 24 years of the service, in that scenario the more future life was available because the corrosion rate was reduced to these numbers 0.266, 0.53, 0.266 and 0.53 mm per year. So the minimum life was 5.88 years. So now that is basically a situation where management or the inspection and corrosion team need to decide, like how they will be managing this equipment. If the damages would be short term, then they have to retire the equipment or they have to do some more preventive measures. But if the corrosion was long term, then they got some more room to manage the equipment. Following damage mechanisms are identified on the basis of service and operating condition. High temperature sulfidation, when temperature is going to 343 degrees Celsius. Water dew point based SD H2SO3 corrosion when operating their normal operation and temperature is 127 degrees Celsius. Welding build-up repairs which might be repeated one, and thermal cyclic fatigue. These are the 4 major damage mechanisms and which are required to be controlled while operating this equipment. High temperature sulfidation as per API 571 section 4.4.2, if the operating condition of a carbon steel is above 260 degrees Celsius, this damage mechanism is applicable. For CBA reactors, aluminizing is done for prevention of sulfidation corrosion. According to Velocity expert opinion, sulfidation is not posing a major threat for integrity of these reactors. Water dew point based on SD H2SO3 corrosion. As per operating manual of CP reactor, lowest operation temperature of CP reactor is 127 degrees Celsius, which is higher than water dew point, and it means that SO2 based corrosion should not be applicable. However, the operating temperature is dropping below water dew point in specific section of the vessel, and some extent of water vapors could be present in saturated form and may combine with SO2 to form H2SO3, and that was the major issue in our opinion. This reason is supposed to be supported by the replacement of CS piping system at downstream of the basically these reactors with SS material, mainly due to internal corrosion problems. At the same time, piping system directly connected to the closed reactor is still working without any major corrosion problem so far. Even operating temperature is significantly higher by closed reactor outlet. Welding built-up repairs are done, which could be a problem if they are done repeatedly. Possibility of repeated repair by welding build-up could cause softening of the base metal. Replica metallography testing has been carried out for such suspected locations, and no deterioration of the material grade has been reported. Client has confirmed that, as per their record, these repairs are not done more than twice. Thermal cycling fatigue. CBA reactors are working under thermal cycle condition. Generally, type of the crack damage mechanisms are caused by thermal or vibration fatigue. So far, no such evidence is reported. It means currently this fatigue related damage mechanism is not active. However, possibility of thermal fatigue related damage mechanism cannot be ruled out. Operational cycles of CBA reactor is completed within 30 hours. Therefore, these reactors would be completing 7,000 cycles in 25 years of design life. Fatigue analysis results are found acceptable at 7,000 thermal cycles. Effect of thermal cycles on hot spray aluminizing is not evident as such. So cost benefit analysis was also done as a part of the study, and the price of the new reactor is 2.7 million dirhams, sorry, it is in dirhams value. And then SS316L, the price of the reactor is 4.1 million dirham, and in Alloy 825, they would be doing, the price is 18.4 million. So replacing cost of 2 CBA reactor with SS316L material is around 4 million. Direct indirect cost of shutdown of each train is about 3.5 million. Therefore, its cost effective if the present CS reactor could be replaced with the new reactor of SS316L. So this was the basically a cost comparison. Conclusion and recommendations. CBA reactors are found fit for service in accordance with API 579 and ASME Section 8 Division 1 and 2 in their present condition. Remnant life of 5.88 years is estimated based on long-term corrosion rates. Control of water dew point above 127 degrees Celsius or so is required. Insurance of close monitoring of outlet temperatures of all reactors. Steam heating coils were installed inside the basically reactors, and those should be more effective during the normal operation. Location of one temperature sensing element could be adjusted near to corroded area, which is basically 12 o'clock location of the reactors. Possibility of corrosion of same location may not be ruled out, and accordingly it may lead to repeated build-up by welding. It is suggested a future repairs could be performed after full verification of quality of the base metal by replica and hardness testing. Monitoring by UT scanning from outside at specified inspection windows with 6 to 12 month frequency. Online monitoring would not be effective in CBA reactors high temperature configuration. Replacement of CS reactors with SS316L new reactors could be more economical option on long-term basis. So we also issued a detailed report, and this shows the basically content of the report and the appendices of the report. So normally all the steps are shown here.